So first I want to do the acknowledgement of country. So I want to acknowledge the first Australians who live on this land, who are the Ngambri and Ngunnawal people. We want to recognize their contributions to this land and their custodianship for tens of thousands of years, and also welcome any Aboriginal or Torres Strait Islander peoples attending the seminar today. So it's my great pleasure to introduce Professor Baoshan Wang. He got his PhD at USTC in 2003, and then went on to work at the Institute of Geophysics at the Chinese Earthquake Administration. But he also went and did a postdoc at Rice University in 2008 and 2009, and that's where we overlapped, both as postdocs working with Feng Lin Nu in Houston. And then in 2019, he became professor at USTC. And he's been there since that time. Most of his work is working on seismic imaging, like me, and also distributed acoustic sensing. And he's also the editor-in-chief of the journal Earthquake Research Advances. And there's some really cool swag that he brought. You guys can take some on your way out. Yeah. So without further ado, he's going to tell us about some of his experiments using DOFS. Let's welcome Baoshan.
Okay, thank you. Okay, good afternoon, and thank Megan for inviting me and for the introduction. Okay. So I'm Baoshan Wang from the University of Science and Technology of China. So today it's my great honor to be here to introduce what we have done during the past 3 to 4 years. Okay, the development of distributed optical fiber sensing and several applications. I was noticed that our audience will be a broader interest, so I will introduce something not limited to geophysics, not limited to seismology, but using the knowledge of seismology. Right? Okay, maybe although I saw a lot of Chinese people here, but maybe a lot of you are not familiar with USTC, the University of Science and Technology of China. So it was founded in 1959. Actually, it belongs to the Chinese Academy of Sciences. So at the very beginning, it's aiming of for the great events and the history of was held as a great event in history of education and the science of China, so in 1970s. And the university was founded in Beijing in 1958, but in 1970, it moved from Beijing to Hebei, where it's located now. Our school is Earth and Space Sciences. It was founded as our university established, so it was also founded in 1959. So our school has 2 departments. One of them is the Department of Geophysics and Space Sciences, and another one is the Department of Geochemistry and Environmental Sciences. So now we offer degrees for bachelor's, master's, and PhD for 5 main geoscience disciplinaries, including space physics, atmospherical science, solid state of geophysics, geochemistry, and environment sciences. So we have now more than 100 faculties. Half of them are full professors, and a lot of young scientists, including K. Wang, who just joined us 3 years ago. So we have mainly geophysics, space physics, atmospherical science, and geochemistry, and some environmental science. So for me, I'm working on seismology. So seismologists study the Earth and the planetaries using seismic stations. So the way we study the Earth, like we pick the watermelon, so we should listen to the vibration of the Earth, of the planet, and then we do the data processing to investigate what's inside of the Earth, and it's like even the oil exploration. So the seismic monitoring is key to reveal the internal structure and the dynamics of the Earth. So especially for the seismologists. So how we sense, how we feel the Earth is of key importance for seismologists. Recently, there are some different instruments. So yesterday I visited the seismological lab in ANU. It's quite fancy. They have different instruments, geophones, have nodal seismometers, have broadband seismometers, and even ocean bottom seismometers. So using this kind of seismometers, we are able to listen to the Earth, to feel the shaking of the Earth at different various places. But with this kind of instruments, we have some limitations. For example, the ocean occupies more than 70% of the surface of the Earth, but we seldom have any observation. Even we have some OBS, but it's quite expensive to deploy and recover. Quite often we lost a lot of OBS station in the ocean. You just mentioned yesterday from the so is there any other way? So during the past 1 or 2 decades, the so-called photonic or fiber optic seismology has developed, which is based on the optical fiber, which is developed which have already been deployed all over the world, all over the Earth, even in the urban area, even in the ocean. So it provides a unique chance for us to listen to the Earth in different way. So the basic principle of the distributed acoustic sensing or distributed optical fiber sensing is we launch a pulse of laser into the fiber and record the backscattering. The light will go straight ahead, which is used for communication. Like we get access to internet when we rely on the optical fiber, which is used in the transmitted lasers. But some very weak, but some laser will be scattered back to where it was injected. If we can detect the phase change and even amplitude change of the scattered laser, we are able to infer what's happening along the fiber. So that's the basic idea. So I don't want to go quite deep. So using this kind of backscattered signal, we are able to measure the temperature and vibration along the fiber. So with very dense and even very broadband. So during the past several years, from our university, we developed our own instrument from the very beginning, from everything, because I have to say our university was listed in the list of the United States. So we cannot export quite fancy stuff. So we have to develop everything by ourselves. This is everything we developed, from the laser source to the detector and to the amplifier and decoder, everything. So during the past several years, we developed 2 instruments. One of them is DTS, distributed temperature sensing instrument, with a temperature resolution up to 0.1 degree and precision to 0.2 degree, with sampling to 1 meter, as low as 1 meter. It means if we connect optic fiber to this machine, then the whole fiber will become thermometer, thousands of thermometers, and then you are able to continuously monitor the temperature change. along the fiber. And also we developed another instrument called USTC DOFS, distributed acoustic sensing. And we are able to sensing the 50 kilometers long cable and with a spacing of 1 meter. And it means if we connect a 50-kilometer long cable to this machine, then you will get 50,000 seismic stations. Okay, but it's one component. It's different from ordinary seismometer. It's only one component. But unfortunately, this kind of machine have a broad frequency band. It can have sensitivity from at least from 1,000 second to 20 kilohertz. So it can cover the frequency band from the ultrasonic, even for the some deformation to the audio. Okay, for the temperature sensing, we applied to the Winter Olympic Games. So why the temperature means? Due to the game, the friction coefficient matters for the competition, for the score, right? So the optimal temperature for the curling competition is minus 10 degrees Celsius. So they should keep the ice to the degree of minus 10. So we deployed optical fiber along the space. So this is a system developed by Tianwei. So we are monitoring the temperature all over the curling site. This is This is actual screenshot of the. We provided the information to the controlling center whether we should increase the temperature. Oh, I'm sorry. Okay, a little bit of delay. Okay, we should increase the temperature or decrease. So we served for the whole Olympic game for 3 months. It works good. For the DOFS, besides the instrument I just talked, we further developed a little bit in 3 different aspects. First, because Megan's group used us a lot, so she has the feeling. The signal to noise ratio of the DOFS will decrease with the length of the fiber. So for the further station, the signal to noise ratio will be lower. The noise will be higher than the near end. The far end will have a lower amplitude noise signal to noise ratio. Recently, we developed a high fidelity instrument which can keep the signal to noise ratio constant for the whole cable. For example, we use the same cable with different two cores connect to the ordinary one and to the new one. So you can see this cable was located in the highway, in the highway. So you can see those lines are the tracks of the cars, and the signal to noise ratio keep constant from the beginning to the end. Okay, so the next direction is the long distance one. Okay, if we have a loop line, so we connected from a loop line, then we are able to sense the fiber up to almost 300 kilometers long. So it's very impressive, right? I think using this kind of technique, we are able to sense maybe the ocean, and we are still working on even longer. So another one is a high resolution one, because most of the DOFS we use has a gauge length from maybe 4 meters to 10 meters. So it's a sufficient number for maybe 90% of applications, but for some of the cases, we need even smaller gauge length. It means more denser seismometers. So this is just to be finished in the laboratory. We are able to get the gauge length lower to maybe 0.3 meters, 30 centimeters. Okay, those instruments have already been used since we developed it in maybe 3 years ago. It has been widely used in China. So, during the Myanmar earthquake occurred last year, so more than 10 stations was in operation in China. So from the China Sea to northeast China and even to the southwest China. So those are stations in operation during that time. Most of them can record the teleseismic event quite well. And the amplitude decrease with distance, but some of them have higher because they are the cable is not well coupled. It's located in some tunnels. And now I will introduce some applications we ongoing or even just finished. Since Megan's group has already done a lot of seismological investigation and even seismic imaging, and I was impressed to observe the avalanche. It's very, very impressive and quite exciting. And I will introduce some applications to atmospherical applications to sounder location, which Megan's group is also working on. And subsea applications and urban infrastructure monitoring. Okay, so for the sounder detecting, the sounder event was well recorded by seismometers. At the very beginning, some of them argue that the signal recorded by the seismometers are surface wave. The sounder hit the ground directly, vertically, and then converted to surface wave. But recently, some argue they are near field body wave. So it's acoustic wave hit close to the station and converted to body wave. But I'm not convinced. Okay, so because most of previous study observe this kind of signal far away from the station. So sometimes because the acoustic wave travels at the speed of maybe 330 meters per second, the surface wave travels the similar speed. So it's hard to distinguish between each other. Okay, so luckily, during our experiment, this experiment was carried in Hefei City, where our university is located. So during this experiment, we used 8 kilometers optical fiber for telecom, and connected our instrument and recast the cable into 3,000 stations. So fortunately, we have lightning occurred very close to the optic fiber. So we are able to record the signal. And also we collected the data from maybe electromagnetic signals from the atmospheric stations. And we are clearly sure we have 6 flash process, 6 flashes. And that's what we observed from the dust, from the optic fiber. It's quite similar to the seismograph as our maybe seismological survey active source seismology. So it's quite close to it. And also you can see some have different curvature. The curvature means the distance, okay? And also we observe some traces like this. Because the fiber is located in the avenue, the main road. So even during the nighttime, we still have some traffic. So the traffic signal can be well recorded. And the signals of the sounders, even, yeah, this is a high pass filter from 40 Hertz. So it's more clear to identify every event. So if you put one record to the speaker, you can hear. Okay, I'm sorry, it doesn't work. You can even hear it as we hear with our ears. Okay, the dominant frequency is larger than 20 Hertz, and we even during the short time period, maybe 15 seconds, we can identify at least 15 sonar events. Okay, each flash process have more than 10 thunderstorms, sonar events. The sounder was generated by the discharge, the electric discharge, and rapidly heat the air, and then generated the ultrasonic wave, and it generally decay to a sonic wave. So if we can locate this acoustic signal, then we are able to deficit the lightning channels. Okay, we located this events, and looks like this. From different point of view, this is from the top, the horizontal axis, and we have the different color means different flash process. And in the middle, we show the height. We have a straight line. In the southern part, the sounder is more diffused. But in the northern part, it's more clustered at the depths of, at the elevation of 3 to 5 kilometers high. And what's the cause? So it's we try to find out, but also we collected the data from the catalog, sounder catalog. They are located somewhere here, different triangles. That's why. So in the southern part, the radar shows the air has higher humidity and more humid, but the northern part is more dry. So it's easier for the discharging occurred from the top to the bottom, to the surface, from the high part to the lower part. And for the west and northern part, the air is more dry, so it can only discharge along a certain elevation. But during our submission, we are challenged by the reviewer. So how can you tell the location is true, right? So you don't have a ground truth event. So how do you know you're correct? Now then we go to another place where we know the sounder, where it is located. So this is located in southern China, in Guangdong province, Guangzhou city. There is a station. They study the triggering light. They shoot a rocket and bring the rocket with a wire and to form a discharge channel. That's how it looks like. Okay, in the middle is the wire. It was fused. Different experiment. In the right part, we see what we observed. Okay. Okay, so I'm sorry to go back a little bit. We deployed a optical fiber along the experiment site, like in yellow here, maybe in 1 kilometer diameter, so it's almost wrong. Then we are able to locate the sonar event like this. Okay, this is a signal from the rocket. We are able to locate, but it's very lower amplitude than we can only locate the lower part. And also we have some high-speed camera. Then we combine the located event together with the camera. They're almost identical, right? So especially this part, in the middle part, if we have strong discharge, but there is no heating, so there is no sonar event in this part because there is a wire, the electric direct transport from here to here. Even the wire was burned. It cannot generate as an acoustic event. Okay, from this point of view, we become more and more confident. At least from our side, from the DAS, the signal from the sonar event are direct acoustic wave rather than surface wave. So we are able to, using this basic hypothesis, we are able to locate this event like this. So it's quite, so maybe in the lower part, below 800 meters, the located event maybe only several tens of meters away from the camera. So it's quite precise. And besides the atmospherical study, we also use it for the subsea. One of the advantages of distributed acoustic sensing is that we can using the existing optical fiber for telecom, even for some telemetry for some deep sea sensors. Yeah, we are able to using existing fiber, so it provides us more opportunity. In 2022, there was a typhoon passing through close to east coast of China. So it passing from the prediction, the typhoon will passing through those two islands. Fortunately, we have optical fiber cable there. So we are able to forming a dense seismic array in subsea to observe the bypassing of the cable. So I'm not going to more detail. So we just developed a method to invert the ocean current with the fiber signals. You can see that this is a typhoon track. This is a cable, optical cable. So just passing through. What we see is that during the passing, before and after the passing of the typhoon, the ocean current change. I think mainly because the typhoon just screws the whole body of water, because the water here is very shallow, maybe 20 to 30 meters deep. So it can be easily scored up by the typhoon. So during this experiment, we use the low frequency signal, maybe below 30 seconds. Okay, it's reliable to, it has a similar response trend as voice, wind speed, and if you are interested, you can go to the for more detail. And another subsea event was the earthquake monitoring. This experiment was carried out in Bohai area. Bohai area is an area with large reservoir of oil and gas. Even in the closed cities, they observed large gold mines. And during 1548, there was an earthquake with magnitude 7. So, and also there are two major faults crossing here. One of them is the Penglai fault. Another one is Tanlu Fault. Tanlu Fault was a major fault in eastern China, which is controlling the regarded maybe as a boundary of two blocks. So but most motivated me is the earthquake swarm during in 2017. A swarm occurred here. Okay, the right side showing the animation of the evolution of the microseismicities. We can see clearly the earthquake migrated from the eastern part to the western part with some speed. Okay, it's pity we don't have the sound. Actually, Zhigang makes some music for this animation. Okay, you can see the migrated from the eastern part and from the deeper part to the shallower part with some speed. Okay. But unfortunately, this was not well recorded because there are only several permanent stations, maybe less than 5. But we are able to locate it with some fancy techniques like a HyperDD and something like that. So I want to ask whether the Earth swarm continuously occur, or between. Actually, there are 3 earthquake swarm occurred from within record 1979 and 2007, 2013. So will there be another swarm, or what's happening during the gap between swarms? So we need a more close observation. Fortunately, we have an optical fiber just above the swarm, 2017 swarm. So we initiated this study. We are trying to cover this area with optical fiber here. Originally, it was 20 kilometers long. Last year, we extended it to 40 kilometers long from even north, and with 40 broadband OBS together. Because you see a lot of faults here and a lot of earthquakes occurred here. So in the morning, as Haran just showed, we are able to record a lot of seismicities, especially the broadband record from a teleseismic event which occurred in 2024. Magnitude moment aware magnitude is 7.3, which is about 1,500 kilometers away. We are able to compare this record from DOFS to seismometers. They are comparable. Why should I compare this? Because I was frequently asked, what's the DOFS observed? And it is comparable to an ordinary seismometer. So from this point, I can tell them it's comparable. And it can be used for shallow, deeper, even whole Earth studies. Okay, the last case. Okay, I'm sorry. From our observations in Hebei City, we observed some tracks like this. During this period, there is no earthquake occurred, but we can see some tracks. Those are tracks generated by cars and trucks. And we developed some technique to measure the velocity of the cars and the number of cars and also the direction. Okay, in the highway, we are able to observe some cars traveling at a speed of maybe 100 kilometers per hour. And because our cable is located in the middle of the highway, so we are able to observe the two-way cars. And then in the urban area, we observe some signal like this. Most of them are at a low speed, maybe someone like this, maybe 220 kilometers per hour. Actually, we take some photo from the bridge. and we match the record, and we see it's generated by the electric bicycle. And we applied this to an actual highway in Hefei City. Okay, and also using this optical fiber, we are able to carry out subsurface imaging for like body check. We can maybe from time to time, one picture per month, we are able to identify whether the road base is in health state or there's some problem. It will be helpful for us to prevent the possible accident and the subsidence. Okay, another one is the subway in China, because in China a lot of construction is ongoing, so it's hard for them to communicate with each other. Sometimes the construct team will drill through the tunnel to the subway. Okay, recently there are some accident occurred in China, so they have to do the check mainly manually. Sorry. That's what they are doing every day once. Okay, going have someone going through this way and that way maybe once a day. It's costly and low efficiency. They also have some blind spot and low accuracy. Fortunately, we have optical fiber in the tunnel, like this in the subway. We have the communication optical fiber. Then from 2024, we carried out a half-year experiment. During this experiment, there are a lot of construction. Those construction was reported. We have different machine in operation. So we are able to construct 100,000 labels for the construction operations. Then we are able to use AI, use artificial intelligence to, those was cooperatively with Zhefeng Li, also in at the USTC. So we are able to record the signals, for example, like this. Even using this kind of cable, it's poorly coupled, but we still can observe the earthquakes. Like for example, this is still the Hualien earthquake, about 1,000 kilometers away. We are able to identify the surface waves and even P wave during the passing of the subways. Okay, like this. And we collected 100,000 labels for different operations. Then we are able to identify on time what's going on. So during the from now on, we have a city scale dense seismic network. Okay. Actually, this was used for subway monitoring, but also we can use it for earthquake study. It can be used for detecting the earthquake because in the year before last year, magnitude 4.7 earthquake occurred in our city. So people get a panic, right? And they are very worried about the possible hazard or something. So now we are able to construct, from now on, we have 300 kilometers long fibers. We use 15 dots and connect to the whole subway cable, and then we are able to monitor it can show in real time whether there is some construction. If I have time, I will show you the website of monitoring. So okay, most of the case here. We have some common interest with MIGA, so we have a lot of other applications, but limited by the time. I would stop here, but it's not not summary, but a perspective. Okay, actually, Brian wrote a booklet about the basic principle of what's the dust and how it can be used for seismological study. And in this book, he wrote, right? Actually, Brian was introduced by Mika about the dust feedback. And he wrote the opportunity provided by dense sampling of the well field by dust, having widely range of geophysical application and a rapid growth community. So you can see from our applications, our application can go beyond geophysics, even beyond geoscience, to engineering and to serve the societies. That's what we are doing now in China. So the last slide will be advertisement. Okay, I'm sorry. Zhigang, who is SSA elected president, and I, actually we are classmates. And we are in charge of a journal of earthquake research advances. So you're welcome to contribute. And we have something there. If you are interested, you can pick up. Okay, thank you. I should stay here. Thank you very much.
Any questions for Baoshan?
Okay.
Always.
Very interesting talk, very impressive. So two questions.
Okay.
The first one is related to instrumentation. So how much is the one like the USTC, for example, DOFS?
Okay, one by one, right?
Yeah.
Okay, that's a good question. Recently, it's about 1 million RMB, Chinese yuan. But if you are interested, I can ship you one for free for using for half a year. Okay?
Well,
Okay, Kelvin knows everything. So if you want to, so you can ask him now.
so move to the second.
Mhm.
I guess the last kind of experiment monitoring actually the city using the subway. So I mean, from your experiment using actually the hang, like fibers, right? They can sense different kind of vibration.
Yeah.
But my question is that can you actually also use that kind of vibration to inform, whether that, for example, if there's a drilling, it's close, like the sensing the structure change of the surrounding material. Is that possible? Or so if it's a drilling.
I'm not sure because it's located maybe 30 meters below the surface. I think it's we are trying to do some imaging, but it's kind of hard. We are still working on this project, but we are able to identify what kind of instrument and how far it is from the cable. And yeah, we are trying to do the imaging, maybe some. And from this, we can see some information. For example, using the record from the local earthquake, we are able to tell the location of faults. So using the Christmas tree, the pine tree shape waveform, then we are able to tell where is the fault possibly located. So we identified at least 2 faults in Hefei City using this record. Yes, please.
So I just wondered, with the example in the city of DAS, can you, so given you have an observation along a cable, and with the assumption that any one vehicle stays on the known roads, can you invert for the actual path of a single vehicle for that information? Is that a well-determined problem?
Actually, we have some hypothesis. First of all, because the fiber is only a linear structure, actually cannot, you're experts. It's hard to locate in maybe even 2 dimensions, right? It can only, maybe it's better to constrain along the location along the cable. And then we are able to track the car. Actually, we are able to track the car for one specific vehicle, but we are not able to identify which lane it was. It's hard, but it's possible, but it's hard. Yeah. Yes, please.
So these are all communications
Mhm.
fibers that are designed to, as much as possible, pass information along them. Have you been looking into manufacturing fibers that are specifically designed to do this kind of measurement? So maybe where you precisely implant some sort of imperfection or reflector in the fiber as you make it, or maybe even sort of some spiral, so you can get more whatever, orthogonal.
Actually, we are testing different kind of fibers. Even using a helical optic fiber, we are trying to recover 3-component informations. Yeah, we are that's we are working on, but actually it's hard because the manufacture of the optic fiber, you should be quite precise about the rotation of even the angle of the telescope. And also you have some trade-off to resolve the 3-dimensional 3-component because you have a gauge length. Okay, the gauge length is average within some distance. So actually, we are trying to resolve the 3-component information from the polarity of the light rather than the phase, but it's still difficult. Yeah, we are going on. And the first thing you mentioned is actually called a microstructure optic fiber. It can be quite sensitive to some information, but the sensing length will be shorter than ordinary optic fiber. So it's possible. So a lot of things we are working on. We have also designed some fibers to measure the vibration and the temperature together, and for deep borehole observations. Yes. Yes, please.
Very interesting talk. I'm curious about you show the Bolivian earthquake record between the DOFS and also the seismometer. I was surprised in the wiggle, like wiggle by wiggle, they are very similar. As far as my understanding, the DOFS is measure the strain rate.
Yeah.
So I don't know like how you compare these two. It's like you do some spatial integral for the strain rate.
Actually, from the raw data, they already look quite similar because the strain rate, the relation between the strain rate and the velocity has proportional to the phase velocity. During certain period, the phase velocity may be stable, like maybe 3.5 kilometers per second. Then if you divide the velocity by the phase velocity, then it's constant. It's just in the frequency, in some frequency band, it's just the difference is between just some constant. So it should be quite similar, but actually there are some details different. Yes, please.
Very quick question. In this plot, you show 3-component seismometer. So how can you get the 3-component seismograph from the DOFS?
Yeah, actually, this was not a 3-component from DOFS. The CHD means station, seismic station. Yeah, we are comparing the DOFS to 3-component seismometer. And we,
Right. You have
we-
one right now.
yeah, the dust signal is the same. Okay, we are able to, currently we are not able to resolve the 3-component signal. Yes.
I've got one question from online audience, from Caroline. Thanks for the last talk. You showing many interesting application of gas. From your perspective, which emerging or unsolved problem is gas most likely to transform in the future?
Transport.
Uh, the
Okay.
ques- The question is from your
The last part.
which emerging or unsolved problem is thus most likely to transform in the future?
Okay, I would like to say too many data. It's how can we deal with this kind of large volume data? Maybe we need to develop some tools like AI based and something like that. So that's my opinion. Right?
Any other questions?
Yes,
One
please.
in the back.
In the application section, you mentioned that the efficient velocity is comparable to the surface velocity. So that you are mentioning the sequence, surface, right?
Yeah, surface wave, because for the near surface, the surface of velocity varies from maybe 100 meters per second to maybe 1,000 meters per second. Usually, ordinarily in city areas, the velocity is around 200 to 400 meters per second. So it's quite close to the acoustic velocity. Yes.
That was lots of questions, but we can continue the questions informally. There's tea and cakes afterwards, but I also wanted to let everybody know that we have reservation for dinner at Verity Lane this evening at 6 p.m. So please just let me or Tanway know if you would like to join us for dinner. We've got a large table, so we should be able to accommodate as many people that want to come. But yes, let's join our hands together and thank
thank you very
Professor
much.
Wang again.
Yeah. Well, thank you. Well,
Thank you.
thank you very much. Oh.